Next, we want to talk about just a couple properties of exponential functions. Here's one of these common examples for us, pretty current. The number of bacteria, we've talked about this before, how bacteria does not grow on a linear rate. Bacteria grows on an exponential rate. That's why it ends up being so dangerous. When the number of bacteria is pretty low down here, it doesn't really matter, but it can get very large very, very quickly. So there's two ways it can either grow or decay. If this number is basically larger than 1, we see this growing effect. If that number ends up being a fraction less than 1, it gets less and less. It's a decay kind of question. So we call that decay because it's actually getting smaller and smaller as we go. This is obviously growth over there. So what we need to do is analyze these functions a little bit more. And I want to get into this expression. We use this obviously much more next year, but this is called an AFA. This is called an advanced function analysis. So advanced function analysis. And what that means is, so AFA, advanced function analysis. What that means is we take a look at our function and we just try to get as much information as we can out of it so we can use it for modeling and problem solving. So some of the basic things, and we'll be more specific next year, of course, but we can get into this a little bit now. So for a function, we are always curious about the domain. So in this case, the domain, all the possible values of x, and because we're talking about number of bacteria and hours, I'm going to start my x off, or t for time, or x, whatever. I'm going to start it off at 0, and it's only going to go in this direction because we don't have negative time. We don't really deal with that function-wise. So I'm going to restrict my domain just to positive values of time, hours, which is fine. So that means my domain, the set of all x such that x is just basically bigger than 0. I didn't include 0 because I could have, but I just said x is bigger than 0. Other than that, x can be any real number. X can be anything. My range then, my resulting values for y has to be bigger than 1 in this case, because here's my y, it starts at 1 and the y takes off in this direction. There's no negative values of y. You can't have a negative number of bacteria. So we're just going to start off at 1 and go in the positive direction. So under part of an advanced function analysis, one thing we look at is the domain and range as part of the analysis. We look for intercepts as well. We look for where does this line hit the x or the y-axis. So in this case, it hits the y-axis at 0, 1. So my y-intercept is 0, 1. And this is a horizontal asymptote. A horizontal asymptote is this line that the function tries to get to but never actually hits. So this function, when I hit it, gets closer and closer to the horizontal asymptote, but it never actually hits it. It never gets there. It doesn't cross. It isn't like, if this is the plane, the function doesn't come down and cross it anywhere. It doesn't hit the x-axis anywhere. It's coming down, it's getting closer and closer and closer, but it's never actually hitting it. So this horizontal line is the line y equals 0. So we identify that as a horizontal asymptote. Okay. So what we're interested in now really is what we call this exponential decay model. We talk so much about exponential decay that's worth identifying a specific model for that. So it's not going to be just a general, y equals whatever, ax to the n. We're going to attach some specific values. So these are the terms that we use and so on, and I'll just explain what they are here. So the left-hand side, y, or the final value, we're just going to use a. So I'm going to use a for amount, because typically with exponential decay, we're talking about an amount of a substance, radioactive material. So we chose a for amount. So I have my a here, and I have my bracket t. Remember, this is function notation. That's not multiply. Okay, this is not, a bracket t is not a times t. A bracket t, so it's not that. A bracket t is function notation. It's like, f of x, but it's written in terms of these terms. So this is just the amount of our element as a function of time. So our final amount as a function of time, right? That should be t, not x. Sorry, make that t. Okay, not x. After t cycles. Now a naught, this little 0 or o called a naught, that's our initial amount. So our starting amount. So we start with, this is what we start with. this is what we end up with. So start is that, and end is that. So we start here and we end there. Okay, T is going to be time, that's obvious. And H is going to be the half-life. H is going to be, that's how long it takes a substance to cut itself in half. Okay, so this is this exponential decay model that we use with expressions. So for example, radioactive decay, uranium-238, which is a sort of an illustration of the atom here, is the most prevalent isotope in uranium ore. It has a half-life of about 4.5 billion years, and that makes it challenging in that once you sort of have some of this uranium-238, it's difficult to store safely, and it's difficult to figure out what to do with because the half-life is so long. It doesn't decay into nothing. It's decaying at a very, very long period of time, so it's tricky to store. Anyway. So suppose I want to write the radioactive decay function for uranium-238. This is what it would look like. So we know it's radioactive decay, so we know it fits our radioactive decay model. I have my final amount that I'll be looking for. I have my initial amount, whatever that is, and it's a half-life. And I put it in terms of billions of years, so 4.5 is my length of time, and here's my T. So the kind of question would be, suppose you start with 100 grams of uranium-238. So 100 grams would go in here, my starting value. Suppose I want to know how much am I going to end up with? What's my final amount going to be? Well, that would be this, tell me my final amount. And all I really need to know is, for how long. If it's 4.5 billion years, who knows? Maybe I say T is, 20 billion years. Okay, depends on what the number is. So that T, that 20, would just sit in there for T. And once you have that, you just use your calculator. You can just go left or right on it. Your calculator should recognize order of operations, and that will give it to you. Okay, so that's it. So take a look at a few questions on page 184.